Hi, in this video we're going to take a look at the next PCBs in the home lighting project. So in the previous video you saw me soldering up the main PCB, and we've also done the relay board and the constant current LED drivers. This time we've got the trailing edge dimmer PCBs. So you've seen me working on various incarnations of prototypes for this particular device, and what this is a PCB that will allow mains powered LED lamps to be dimmed. So unlike traditional dimmers, the AC waveform needs to be chopped in a particular way so that you can control the brightness without creating a whole lot of harmonics and also a lot of problems for the LED driver that is typically built into dimmable LED light replacements. So you can see in this design I've gone for the same kind of finish as with all of the other PCBs. So this project's entirely made from PCBs with the blue finish, with the immersion gold finish on the exposed copper pads. And you can see we've got a few interesting design traits in this PCB. So we've got an isolation barrier that's afforded by some slots in the PCB. You can't see it very well against the blue background actually, but there's a slot that goes almost right the way down this bit, so it is potentially a little bit weak, but with the 1.6mm board we've still got a good amount of strength there, so I'm not too concerned about that. We've got a few slots here on this side, so basically from this point to here is at mains potential, and on the left hand side of the board is all the stuff that's at separated extra low voltage. It will be the same potential as all of the electronics on the main board and completely safe to touch. So basically what we've got is a DC to DC converter that's fully isolated, a gate driver for the MOSFETs that's fully isolated, and also an opto isolator which allows us to look and find the zero crossing point on the AC waveform. So here's our schematic, and it's separated from the mains voltage side to the separated extra low voltage side by these three components. So just having a little look at the schematic here, it takes in the 12 volts from the separated extra low voltage side. We've got a isolated DC to DC converter which then provides us with an isolated 12 volt supply for use on the mains reference side of the schematic. We've got a couple of power LEDs and status LEDs, and we've also got some capacitors here just for the 12 volt and 3.3 volt rails that are coming from the main PCB. Here we've got our 10-pin connector which goes onto the main board, and we've also got our two ID resistors which tell the main board that this is a trailing edge dimmer module. On this side of the schematic is the actual part that does the AC control, and so our AC comes in on pins 1 and 2, so line and neutral, goes through a fuse. It then goes to this pair of MOSFETs, so these are two N-channel MOSFETs wired with the sources connected together, and that allows us to switch both sides of the AC waveform depending on at which point we turn on the gate. We've got a couple of Zener diodes and transorbs to try and protect the gate and also the MOSFETs from transient voltages. We've got a snubber network to try and reduce some of the harmonics that are produced when switching off the AC part the way through the AC waveform. And we've also got a varistor which is there to try and clamp the voltage in case we see excessive voltage and stop it damaging these MOSFETs. At the bottom you'll see that we've got a slightly simplified schematic compared to the prototypes, and what we're using here, instead of the bridge rectifier and standard optocoupler, what we've actually got is a AC optocoupler, which is essentially just a specific optocoupler with two infrared LEDs in inverse parallel, which negates the need for an external bridge rectifier. So we've got a few less parts on the PCB, and then we've just got a couple of resistors that's driving that. On this side of the schematic we've got a Schmitt trigger buffer to try and clean up the signal coming from the transistor side of the optocoupler, and then that goes back into our main board to determine where the zero crossing point is on the AC waveform. Right, so here we are with the Eakins microscope, and I think there is a little bit of a difference compared to my usual microscope. Not through the eyepieces. The optical image quality that I'm seeing through the eyepieces is perfect, but I think just the difference in camera is making all of the difference. But what we're going to do to start with is put a bit of solder on one of the pads for each component as always. I'm going to hand assemble this PCB to start with, and then any future ones I'll do with the stencil, but yeah, it doesn't really make sense to try and get the solder paste out and all of that just for one PCB, especially when there's only a few surface mount parts. So here's our completed PCB, and I think it looks fairly neat. I've opted for a polyfuse up here rather than a standard fuse for now, although I do have some 2 amp standard fuses. Unfortunately the terminal block went in very slightly wonky, but you can see I arranged the TO220 packages so that if we do need to add any heat sinking, it's very easy just to add a little piece of metal. We've got about 4 or 5 millimeters gap there between the TO220 packages and this capacitor here. So we can quite easily add some heat sinking in there. So what we'll just do now is measure the insulation resistance between this side of the board and this side of the board, just to make sure that we've got isolation between the two sides. So what we're going to do is apply 500 volts to one of the terminals on this side and measure the current effectively through the board, and that gives us the impedance using Ohm's law. So if we just put this across the pins on this side and put the other probe here, and then we could run the test. And you can see that was greater than 500 megohms at 500 volts. So that implies that we have very good isolation between the two sides, and we can now plug this into the main board and test it. So what I've done is I've transferred the firmware from the development board that I was working on previously. So this should all work as it did before. The only thing I've had to do is just change some of the constants because we're running at a slightly different oscillator speed. And then also I've been working on the firmware to interface with the GPIO expanders, so we've got a bit of a library going now to interface with the switch inputs. And what we've got now is, if you can imagine, we've got all 4 boards plugged in. If you look from the side, we've got sort of 2 stacks of terminal blocks, so nothing is getting in the way of anything else. So these are all our switch inputs, and then we're going to have all our AC powered and outputs to LEDs and that kind of thing at the top here. So that's that. I've also just wired in the switch that we were using last time. I've not tested any of this yet, so this is the first time that we're going to be running this. So what I will do is I'll connect all this up to the isolation transformer. We saw previously that when we were looking at the waveforms, it introduced some artifacts due to the fact that it has quite a high inductance on the primary coil. So just to test it, first of all, to make sure that the whole thing doesn't blow up, we'll try it on the isolation transformer. And then if we do some further testing in this video, we'll look at the waveforms with it plugged in direct to the mains. And what we'll do is we'll use the isolated probes. And to start with, we're just going to test this with a standard incandescent lamp. So a resistive load is ideal for testing first of all because it doesn't have any nasty transients that it's going to generate. So at least it should be relatively difficult to blow this up as a result of the load. We just want to check that the operation is correct on this to start with. Right, so I've connected up the DC supply to the PCB, and we've got some flashing lights here. So this first one is indicating that the firmware is running properly on the microcontroller. And then we've got another LED which isn't lit at the moment, but that's tied in with the AC zero crossing point detection circuitry and firmware. And when it's latched on, we should see that illuminate. So we can turn on the AC supply now. And we've got 230 volts coming in. And actually, I think what I'm seeing, I'm not sure if it's coming out on camera, is that blue LED is flickering just a little bit. Let me turn down the AC supply a little bit. and that flickering gets worse. So what I'm thinking is that maybe there's not quite enough current getting through to bias the transistor on this side of the zero crossing AC optocoupler. Previously, well, first of all, I've not used this particular design with the AC optocoupler and the two 100k resistors, but previously also these resistors were much lower in value, and what I wanted to do was try and reduce the dissipation in these resistors so that we weren't just burning power detecting the zero crossing point. But it looks like potentially that there's an error just there and we're not quite getting consistent operation. We should still be able to turn the light on, but what we might see is that the light starts to flicker a little bit. So let's have a look. And so it comes up to full brightness okay. Let's try dimming it down a little bit. And yeah, the flickering is becoming apparent on the bulb. So we've definitely got an issue here. I just need to check that it's not the firmware first. What we'll also do is just get the oscilloscope out and just probe the output of the optocoupler here and just check that it is glitching at that point and I haven't made a mistake in the firmware. Right, so I've been doing some debugging and there's been a few red herrings along the way when I've been probing various things, but I've tested the board with AC voltages from 120 up to 250 volts, and we are getting good biasing of the infrared LED on the zero crossing optocoupler. So all of the component selection appears to be fine, and if we look at the output from the zero crossing Schmidt trigger, in fact we can see it on the oscilloscope, we're actually getting a really good signal that's straddling the AC waveform coming in. So we've got two differential probes connected up, both of the mixed sigs. The yellow one is connected to the incoming AC, and then the other one, which is this blue trace here, which is ramping up with the AC waveform, is connected to the lamp. And what I seem to have found is potentially a silicon issue or something to do with the compiler. I'm not sure yet, but basically the way that I'm detecting where the zero crossing point is, we've got the interrupt on pin change enabled on that microcontroller. So whenever there's a change in the state of the pin, it triggers an interrupt, and then you're able to process the the timings here and work out where the zero crossing point actually is. Now, because of the particular setup of the interrupt on change, you don't get an indication from any of the status registers whether it was a rising or a falling edge. So what you have to do is you have to then go and sample the pin to find out whether it was a rising edge or a falling edge. And the very first thing that I do in the interrupt at this point here is read the pin to see whether the pin is now high or whether it's still low. And for whatever reason, occasionally it was reading the pin as being low, and that was causing the skipping of various pulses, and that was what was causing the flickering and false triggering. Adding a very small delay, so just I think I put in 25 clock cycles to start with, just to test whether that was the issue. It's now completely stable, so it doesn't look like you can read that port pin immediately after the interrupt is triggered. And having a little look at the datasheet, it's potentially a completely different section of circuitry that deals with the interrupt on change than the port registers. So maybe there's something to do with those port registers that is causing us a few problems. However, it seems to be working fine now, and you can see here the point that we're turning on the gate is bang in the middle here. So if I zoom in a little bit, you can see we're triggering the gate bang on the zero crossing point, which is actually where the dV by dt of this signal is the greatest. So we're getting really good timing here to get it bang on point. So we're doing a little bit of maths here to work out basically where the zero crossing point is. We're sampling here and here, working out the difference, and essentially dividing it by 2 to work out exactly where the zero crossing point is. So I'm quite happy with how this is working now, at least with the incandescent lamp. I'm able to dim this down and up, and everything in between. There's a little bit of firmware work still to do to tidy everything up, but you can see that we've got good control of the lamp. So the next thing that I need to do is plug in the Philips LED lamp, which is what I was testing with last time, to make sure that we're able to control this capacitive load correctly. Right, so we've got the LED lamp plugged in now, and you can see that we're getting a little bit of leakage through the lamp, and that is because we have a snubber network on this PCB which is attempting to reduce any transients that might be occurring on the switching edges from these very fast switching MOSFETs. But when we turn it on, we should see that disappear and we should see our normal waveform. And so we're on about half brightness there, and if we zoom in, we can see we're getting a really nice waveform. You'll notice it's quite different to the incandescent lamp, so although it's completely following the waveform on the switch on, and it's still triggering exactly at the zero crossing point, so we're getting minimal switching losses in these MOSFETs. At the point where it switches off, you can see that it's actually decaying quite slowly as opposed to the rapid switch off. That's partly to do with our snubber network and the relatively low load, but also the LED driver in the LED lamp does have some built-in capacitance, not a significant amount because obviously with an AC waveform going in, we wouldn't want to try and dump charge on the opposite part of the AC cycle, but there's just enough there to bring it down slowly and reduce any transients. And actually this is a really good looking waveform. This means that we're not getting any noise or any significant noise coming from the PCB or the lamp due to the dimmer process. All we'll be getting is the noise associated with the actual electronics in this lamp. But because we've got relatively nice smooth waveforms, we're doing a good job of controlling the AC going into the lamp, and therefore this seems to be working quite well. And unlike the standard dimmers that you can get, we're able to control this lamp right down to minimum brightness and all the way up to maximum power. So in one of my earlier videos I demonstrated that the standard dimmer switches that you'd normally have in your wall steal some of the power from the lamp in order to operate, and therefore you never actually get full brightness from them. In this particular design you can get absolutely full power, but also you can dim the lamp right down to much lower levels than you'd ever be able to with a standard dimmer switch, because this has its own power source, and it's not trying to steal power through the lamp or from the lamp. So that all seems to be working really well. I'm quite happy with how this is looking, and the other nice thing is that I was slightly worried that we were going to have to make some changes to some of the electronics on this PCB. In fact, it's all working exactly as intended, which now means that I can build up the rest of these PCBs in a nice assembly line. Obviously, producing one-off PCBs is a little bit of a faff because you have to keep getting out various components. I've got a whole load of these to build up, and therefore I can just set up all of the components and just get a production line going and build them all nice and easily. Right, so this is getting quite exciting now because we're getting very close to the point where I'm going to be able to install this in the house. Obviously this part is already working, so if I just want to dim some lights, we're at the point where I can do that, although it's a little bit overkill just for light dimming unless we're incorporating some of the other features. So one of the things that I was thinking of doing with this is tying it in with the alarm system, so that my wife, who always leaves the lights on in the house whenever she leaves in the morning, it can tell that the alarm's set and then turn off the lights after a preset period of time. We could also incorporate some microwave sensors, so occupancy sensors, so that if there's no movement in the room for a certain period of time, we could also turn the lights off. But there's a few other interesting things that I could explore with this design. And I've also got a couple more modules. One of them I've already got the PCB for, so that's for some RGB LED tape and that kind of thing, so simple PWM control of those. And I'm also thinking about making a module to control DMX lights. If you watched some of my early videos this year, I bought some LED linear lights that are DMX controlled, and they're really nice actually. They just run from a 24 volt supply, they've got all the thermal management and everything built in, but they just need a DMX control to control them. And so I'm thinking about just creating a module that will plug in interfaces with the SPI bus, but then the microcontroller on that board would then deal with the DMX control, because it's relatively CPU intensive to keep firing stuff out from the memory on the DMX bus. So a few more things that we can explore. I've also bought a rather large cabinet. I think it's probably about 80 centimeters by 60 centimeters, something like that. It might be a little bit smaller than that, but a DIN rail cabinet. So the plan is to mount that up in the loft and then have a whole series of these PCBs mounted on the back plane of it, and also have on the DIN rails the 12 and 24 volt power supplies for the various things that are going to be connected to it. So it's all one self-contained unit. We'll have the DIN rail terminals and everything in there so that we can reconfigure things as and when we need. But the upstairs lighting lends itself very well to testing this whole system out, because obviously all of the electrical wiring is available in the loft very easily, and we can see how we get on and easily reconfigure things. And I can easily set things back if I have that DIN rail cabinet where I can take these out of service and just connect things up directly if I need to revert everything back. So some interesting things to explore coming up. I do need to do quite a lot of firmware work to tidy everything up and make this whole thing robust, because the last thing I want is lights turning on in the middle of the night, or the lights not working when you need them. So I do need to make that firmware as robust as possible, so that's going to be my task coming up. But we'll continue with the videos on the remaining modules and testing as we go. So hopefully you found this video interesting. I'll put the links for the Mixig differential probes in case you didn't see those in my previous video, and also to the microscope that I used in this particular video. But anyway, hope you found this video useful, and until next time, thanks for watching.